So for the next 2 days, we're going to spend reviewing sequences and series, notation, yada, yada, yada. Okay? So, find the pattern. What's the pattern?
Plus 4.
Add 4. What's the formula?
N equals a to the n plus 2 all in parentheses plus 4 times a to the n plus 1.
Huh? No.
It's 3 plus 4 times n minus 1.
Yes. You don't want a to the n in an explicitly defined sequence. Okay. Does it work? This is their theory. Does it work? Let's try it. If I plug in 1 for n, I get 4 times 0, which is 0 plus 3. Does that work? If I plug in 2 for n, 2 minus 1 is 1. 3 plus 4 is? Does it work? You may remember the explicitly defined formula for an arithmetic sequence is the first term plus the common difference times n minus 1. Or you might have just figured it out. Maybe, Joseph, you were doing recursive. What does it mean to be recursively defined?
It's previous term.
It is defined upon a previous term. That's why it's called recursive. We've got to use what's given to us before. So a sub n would equal the term before it, which would be a subscript n minus 1, plus 4. So it would be the term before plus 4. So there are 2 ways to define a sequence. There's a recursive formula and an explicit formula. Recursive sequence defines one or more of the first few terms, and then all other terms are defined using previous terms. Sometimes you can just, like in arithmetic, you can define one term and then use that. Sometimes you have to define more than one to begin with, like y'all may remember learning Fibonacci sequence. It defined a sub 0 or a sub 1 and a sub 2, and then every term after that was found by adding the previous 2 terms. An explicit formula is a formula that allows direct computation of any term for a sequence. In other words, if I want to find the 100th term, I put 100 in for n and I've got it. I'm probably not going to work these 2 problems at the bottom, but I'm just going to tell you how to do them. To find terms in a recursive sequence, you have to know previous terms. So in a recursive sequence, finding the 100th term is hard work. Why? I got to go through every single one before that. Unless I can write an explicit formula, recursive is difficult for a human to do. Where do you think recursive formulas have their place? Computers, calculators. Have y'all ever used Excel?
Yes.
You know that drag and drop button? That's a recursive formula. Do this over and over and over again, where you drag, know what I'm talking about, the little, like you drag the box. I use it all the time when I use Excel. Okay, so we can, and then explicit formulas, the beauty in an explicit formula is that you can find any term. The bad thing about an explicit formula is sometimes it's hard to write. Not with arithmetic, but sometimes with other sequences, explicit's hard to write. Okay, any questions about this slide? Okay, arithmetic sequences. You probably already figured this out. But arithmetic sequences are sequences in which you add or subtract the same number from the previous term to get the next term. The number that you add or subtract is called the common difference. Arithmetic sequences are linear, and the common difference is the slope. This is the explicit formula for any arithmetic sequence. It's the first term plus the common difference times n minus 1. Oops, sorry. The recursive formula is the previous term plus the common difference. I'm not going to go through all of these examples. This is about 4 days worth of Algebra 2 slides pulled into one. So we're not going to go through every example, but Y'all remember learning this now? Kind of. Is it okay so far? But we probably won't do every Algebra 2 example. We'll do some.
What do we spend on these?
About a week.
How long do we spend on arithmetic specifically?
A day.
Okay, good.
But today we're doing arithmetic and geometric together, and then tomorrow we'll pick up what we don't finish. So we're going to shove a week into 2 days.
That's fine.
It shouldn't be bad. Find the nth term of the arithmetic sequence. First term is 7, common difference. Right. 7 plus 4 times n minus 1. That's how you do an arithmetic explicit formula. Recursive formula, you would do the term before plus 4. So that's how you write an arithmetic sequence.
When you do recursive, you have to define the initial.
Yeah, you probably should define the initial as well. We'll skip that one. Okay, when we did this slide, I was trying to get you to come up with this next formula. For today, I'm just going to tell you the next formula. Sum of an arithmetic sequence is the first term plus the last term times n divided by 2. Essentially, you average the first and the last term, and you multiply it by how many terms there are, and that gives you the sum. You may remember from Algebra 2, I told you the story about Gauss, where he was adding it. Y'all remember? It's been a long time, but you remember.
His teachers told him to write down and do that addition.
Yes, and she got mad at him.
You cheated. You're an idiot.
But he was right, wasn't he? Okay. So if we wanted to find the sum of the first 30 terms of this sequence, we would need the first term, we would need the last term, and then we'd need to multiply it by 15, right? 30 divided by 2, and that's how you find the sum of an arithmetic sequence.
So would n be 0 or 1?
1.
What would it be in that?
30. Because there are 30 n's the number of terms.
Looking at the sequence 3 and
Yeah, so you would plug in 1 into that and you would get 8. You would plug in 30 into that and you would get 95. And you'd multiply that by 15. So that's the sum of an arithmetic sequence formula. If you were still taking ACT, that formula would be quite important to you. You are not, so. Do what? Yeah. That formula is not particularly important in calculus. The big thing we're getting back is the gist of the notion of what a sequence is. Okay, we're not really doing the sequence, the algebra part of it. I'm going to skip that word problem and skip that word problem. Okay, so next, what's this pattern? Multiplied by 2.
So this is geometric then?
This is geometric. So day number 2 in Algebra 2. Oh, it might have been day 3. I don't know. Write the formula for the nth term of the sequence. Well, I guess I should let y'all think. I will let you think. Maybe you can figure it out.
Just a little too. Okay.
Yep, no problem there.
I'm going to do it again.
Okay. As long as it's equivalent, Jessica, you're good.
3 times n to the root of 3 times 2 to the n minus 1.
Very good.
I was thinking, okay.
What do y'all think? Try it, see if it works.
I actually remember these.
You do?
Kind of, yeah.
Cool.
Just the basic thinking how to do it. That's what I'm going to.
It's been a while, and it's not something that, like I said, the skills you need for this chapter is not like the nasty sequence series problems. It's the basic understanding of what a sequence is. We got to remind ourselves what summation notation is. The n minus 1. Why is this the formula?
Because you're multiplying by 2 and
You're multiplying by 2, but you don't want to multiply by 2 the first time.
Yeah.
But you do want to multiply by 2 the second time. And then the third time you want to multiply by 2 twice. And multiply by 2 however many times your number of the sequence is. Recursive formula is a lot easier. The previous term times 2. Everyone agree with that? So recursive formulas are often easier to write, but they aren't often as useful as explicit formulas. This is a geometric sequence, yes. So, geometric sequence. A sequence of values follows a pattern of multiplying a fixed amount, not 0, times each term to arrive at the following term is referred to as a geometric sequence. The number multiplied each time is constant. The fixed amount multiplied is called the common ratio. To find the common ratio, you divide the second term by the first term. In general, your formula, your explicit formula, is the first term times the common ratio to the n minus 1. And your recursive formula is the previous term times the common ratio. And this is a geometric sequence. These are the two sequences we learned that were special because we kind of could find a pattern for them that worked all the time. Any other sequence that's not arithmetic or geometric is just one we'll have to think about in and of itself. The hardest part of writing the equation, the explicit formula, if it's not arithmetic or geometric, is thinking through how you can write an explicit formula. And that is a challenge both in non-calculus and in calculus, and it takes some creativity sometimes. Okay. I'm not going to do that example unless y'all feel like we need to. Do we need to do an example? Yes, next is geometric sum. Skip that. Common ratio, one term, that's good. Okay, sum of a geometric sequence. To find the sum of a geometric sequence, you can use this formula. The first term times 1 minus r to the n divided by 1 minus r. This is called the nth partial sum, and the reason it's called a partial sum, which we wouldn't have talked about that in Algebra 2, I probably just kind of skimmed over it, but the reason it's called a partial sum, if you have a true sequence that goes on forever, if you stop at any point and do a sum, you're only doing a partial sum of the sequence because you're not summing up the entire sequence, you're just summing up part of it.
Sequences go on for infinity. What will the sum be?
Good question. Crazy calculus thought.
Which means we're going to learn that no, it's not.
We're actually going to learn that. You even learned it in Algebra 2, except you just didn't know why. Quick question. if r is less than 1, okay, so r is a ratio that I'm multiplying by that's less than 1. So give me a number less than 1.
It's going to be given.
A half. If I do the limit as n approaches infinity of this sequence here, would you agree that this piece would go to 0 if r is less than 1? And so the infinite sum of a geometric sequence would be a1 divided by 1 minus r. Now, of course, that only works if r is less than 1. If r is greater than 1, then you would have an infinite answer, right? In calculus, we call this a converging sequence. And if r is greater than 1, we would say it diverges, right? So, interesting thought. By the way, I actually taught you that in Algebra 1, or Algebra 2. You just didn't really know what I was talking about. A geometric series is called convergent. A series is a sum of a sequence, by the way. If the common ratio is between -1 and 1, in which case the infinite sum can be calculated, and it's just the first term divided by 1 minus r. And you can now see why. In Algebra 2, you just had to memorize the formula and go, okay, because Miss King said so, this is what it is. But now you can see why that limit would exist, and you can sum up an infinite amount of numbers. Now, I do want to show you this in real-world application-wise, because on paper, I heard some of you going, you can't sum an infinite amount of numbers, right? Some of you are still a little shaky on that. But say I'm walking from here to that wall, and I go halfway there. And then I go halfway again, and halfway again, and halfway again, and continue to go halfway. Wouldn't that be a geometric sequence? Am I ever going to actually get to the wall? Am I going to get so close that we might as well say in real world times I got to the wall? That would be the sum of that geometric sequence. It would be the distance from here to the wall. Because I get there eventually. So that's a real world example of a sum of an infinite sequence. Does that make sense? Anyway. So we could determine if the sequence converges or diverges. If r is a half, does it converge or diverge? Converges because r is less than 1. Here? What am I multiplying by every time? Converges, right? This one down here. Diverges. Even though it's a negative, it is less than, or it's less than -1. It's outside -1 to 1, so that would diverge. We could look at the limit, and we'll talk about that later. Evaluating it, you just plug it into the formula, but we're going to do a little better than that and get a little more specific. I showed you in Algebra 2, just for the fun of it, how you could convert an infinite fraction into a, or an infinite decimal into a fraction using sequences. Do y'all remember that? Because this is 0.3 plus 0.03 plus 0.003. Does everyone agree with that? What's the common multiplier here? Everyone agree? I'm multiplying by 1/10. So what's my common ratio? 1/10. So my first term is 0.3 divided by 1 minus 1/10. What is 1 minus 1/10? 9/10. So I could multiply by 10/9. Does everyone agree? This is 3/10 times 10/9, which is 1/3. You all knew that was a third. But you didn't know this one, right? And you could do the same thing, the 0.123. I don't. We would do the first term, I would call it 0.123, the whole repeating portion, plus 0.0000123, and we could go on. This time we're multiplying by what? Thousandths, so it would be 0.123 or 123 1,000ths divided by 1 minus 1 1,000th, right? Which is 123 1,000ths times 1,000 over 999. Is that right?
41 over 333.
So 41 over 333. So, and interesting. Don't know that you need to know it for calculus, but interesting nonetheless that you can go backtrack and find out every repeating decimal is a fraction because we can find the sum of that finite sequence or that infinite sequence. Factorial, you need to know what a factorial is. N factorial is n times n minus 1 all the way down to multiplied by 1. 0 factorial is 1. And that's what a factorial is. How are we feeling on pace? Okay, as far as just picking up some old stuff that we learned a long time ago. Yeah, doing okay. We could simplify factorials without picking up a calculator. What do you know about 8 factorial over 6 factorial? What's going to happen to a lot of that?
It's going to do 6 factorial times, so all it was 8 times 7 on top.
Does everyone agree with that? The 6 factorial part will cancel. The 6 times 5 times 4 times 3 times 2 times 1 will cancel on top and bottom. I could write it all out. And so 8 divided by 2 is 4. 4 times 7 is 28. So I can do that really fast in my head. Not because I'm multiplying 6 times 5 times 4 times 3 times 2 times 1 in my head, because I am not. What about this one? The 6 factorial, the 5 on down will cancel with the 5 factorial. Everyone agree? 2 factorial is just 2 times 1. 3 factorial is 3 times 2. So the 3 times 2 will cancel. And I just get 2. What about n factorial over n minus 1 factorial? N. Questions? What? No? We're good? Okay. I just told you this last, it's just complete, or in Algebra 2, not anything you need to know right now, but Pascal's triangle can be generated using this. Pascal's triangle was the numbers in front of the expansion of n plus 1 squared or cubed. Anyway.
We did something like that in chemistry or something.
Maybe. Okay, summation notation. Summation notation. If I have the sum of n from n equals 1 to 4, The way you work that is you take this n value and you plug it in for n. And then you go up in integer values. So you go to 2 and plug in 2, then you plug in 3, then you plug in 4. And you stop when you get to this number. You stop when you plug in the 4. And that's how a summation notation works. So, we're going to do a couple to see if you understand how it works. This is the explicit formula of some sequence, and this is the terms that I'm adding in that explicit formula. So I'm going to plug in 1, and I get, and then I'm going to plug in 2, and I get, then I'm going to plug in 3, and I get, and I'm going to plug in 4, and I get, and I'm going to stop. Why am I going to stop? Because 4 is where I stop. Any questions about that? Do I need to do any more of those? That's how summation notation works. I remember when Algebra 2 was hard.
No, I don't. Too long ago.
It's a long time ago, wasn't it?
It was 2 years ago. It was 2 years ago.
You can do summations in your calculator. We already did this by hand, except we didn't add, but you can add. Your calculator will also do summations. Both the TI-84 and the TI-89 will both do summations. The TI-89 looks right as far as notation. I don't know. Does the 84 look right too when you use the summation? So, they both do summations.
This actually has actually F4, F3, F4.
F3 number 4 in the TI-89 is the summation.
I don't know what looks like.
You type in the 89. You type k squared minus 3, comma k, comma 1, comma 4. If I remember correctly. Don't know what I mean by that. I think. Check it. See if it works. It's been about 10 years since I've typed that in my calculator.
Yes.
That work? Yeah, perfect. Yep. Just like integral.
Okay. Yeah, okay, that works.
What I would assume in an integral have similar.
Because they're both just adding together.
Yeah, isn't an integral also a sum? Isn't it an infinite sum? Write in summation notation. We'll do a couple. Now, could these get hard? Yes, because essentially what you're doing is you're writing the explicit formula of the sequence. If it's arithmetic or geometric, it's easy. If it's not arithmetic or geometric, then it's going to take thought. And there's no, if you remember from Algebra 2, the place that this got hard is when it wasn't arithmetic or geometric and you had to be creative to come up with the explicit formula. The first one is not arithmetic or geometric. Would you agree? But what is the explicit formula? It's not actually too bad. 1 over n or n plus 1. Both of those would work. Why would both of those work? Why did I agree with both of you?
Because
You could start on a different spot, right? If it's 1 over n, then I'm starting at n equals 1. Agreed? Going to 5. If you do n plus 1 on the bottom, then you're starting at 0 and going to 4. Okay. Sounds great, right? You can do either one. So that was neither arithmetic or geometric, but we were still able to find the explicit formula. This one's the same formula, except I'm going from, let's call it k instead of n. K equals 1 to n. Why did I do a variable swap there?
Because you would be going from n to n.
Because I need an n at the top, so I didn't want to use that as my variable.
Is it kind of like integrals? Like, what if your goal is the same place? Or you just put that number there?
Probably similar to integrals, we'd call it a spelling error. Like if you did use the same, is that what you mean?
If it's all like, you know, if you have a 0 on the bottom and 0 on the top, you get.
Oh, if you don't go anywhere, yeah.
Or is it a number like if you get, would h just be 1 over n?
So if we went from n to n, I guess it would be 1 over n. Yeah, if you went from n to n. All right, let's see. What are we doing on the next one? So we're doing 1 times 2 times 3 times 4. I agree. How are we going to write that? I'll give you a minute because this is where they get tough. Quick question. Let's rewrite this sequences without multiplying it out. So the first one is 1. The second one is 1 times 2. Does everyone agree? What's the third one? That, if it were just geometric, if I were multiplying by the same thing every time, I could. Ah, factorial? 1 factorial, 2 factorial, 3 factorial, 4 factorial?
Those would be the factorials.
That's tough enough. Did it help to write it out in its unsimplified form once you found the pattern? Okay. What am I doing this time? Multiplying by 3. Now this is one, Logan, as soon as you figure out you're multiplying by 3, you can quit thinking so hard and use the geometric 2 times 3 to the n minus 1. Like recursive, maybe? Might get you a recursive formula, but for a sum, you'll need explicit. But I'm not saying, I mean, there are sometimes other ways to write it. From 1 to, what am I going to? 4? 3 cubed is 27. 27 times 2 is 54 works. Okay. We could do more examples of writing sequences Probably more beneficial to be able to write them explicit for what we're about to do than recursive, and we kind of just did some examples on that.
We have to start that last one here, just going before this. We start that at 2, or we just start that at 1?
Good question. The one I just wrote.
Yeah.
1 minus 1 would be 0. Anything to the 0 power is 1. 1 times 2 is 2. So 1 would be a good start. Do you see how I checked that? I just plugged it in to see if it comes out. Okay. The only new slide for the day is convergence of a sequence. This is the only thing you've never seen before. Although you kind of saw it on that geometric sequence. If you have, though this is a sequence converging, not a sum of a sequence converging, we'll have some work to do with sums of sequences converging. Just a plain sequence, whether a sequence converges or not. If the explicit formula converges as n approaches infinity, then the sequence is said to converge to a number. If not, it diverges. Does this feel like a limit to you? So, the first one. So if the limit is n approaches infinity of the explicit formula of a sequence is a number, then the sequence converges to that number. If not, then the sequence diverges. So number 1, the limit as n approaches infinity of this sequence, why does it equal 3? Since we're going to infinity, we look at the highest powers on top and bottom. This will feel like a little bit of limit review. If you read this chapter where this is taught in your calculus textbook, where this sequence stuff is taught, a chapter just following this teaches L'Hopital's rule. So you can see why they would do that, because they're using limits again. Okay, the limit as n approaches infinity here. Good question, isn't it? Strange, isn't it? Do what?
Infinity minus 1 and infinity plus 1 are the same number. But it's 1.
But do you end where you've done a positive and a negative, or do you end on a positive? It's a good question. And we're not adding, we're just going.
So that would be like times 1, negative 1 times infinity, like to the infinity is...
As you get really, really big, do you agree that you bounce back and forth between negative 1 and 1? Do you go to exactly one number? You bounce back and forth between negative 1 and 1, agree? Depending on even or odd. When n's even, you go to positive and infinity, or positive 1. When n is negative, you go... So this diverges. Quick question. What if this had been an n squared on the bottom? Then it would go to 0, because does it matter if it's positive or negative? No. So if that is 1, then that diverges. But if it's 0, it converges to 0. So that's interesting. What kind of sequence is this? Recursively defined. What type? Arithmetic. So I am taking 5 and adding 2, and then 2, and then 2, and then 2. Does this sequence converge?
No.
Why not?
Because it's just
It's just going to keep adding numbers to it. The explicit formula for this is 5 plus 2 times n minus 1. Does everyone agree? And as n approaches infinity, this approaches infinity. Right? Would a geometric sequence converge?
unless it's the fraction.
Maybe. Right? If the number that we're multiplying by is a fraction, then it would converge to 0. So it depends. Okay, this is your homework. It is due Wednesday. Tomorrow in class, we will not work on this. It's just a 2-night homework assignment. You get to work on it over 2 nights. It really could have probably been a 1-night assignment. Over the next 2 days in class, we are not going to have any additional homework, and I'm not even going to make you take notes. You're just going to sit and listen to me talk about what we're going to talk about this chapter. It's going to be an interesting couple of days where we do a chapter overview exploration. So that at home, next 2 days, come with open ears, ready to learn, but you don't have to do any homework. How do we feel about our sequence review? Good? Okay, this is all review except for 32 through 40. I think those are the convergence or divergence.